In this section, we'll be discussing applications of sets. We're skipping most of Chapter 2, which introduces sets and some basic stuff about sets, and we're just going to skip straight to, what do we use them for? So I'm going to summarize all the basic facts that we kind of need from the earlier sections here. All right. First example, let's say that we have a survey of 1,000 students, and that in that survey they find that 740 students like dogs, 530 students like cats, and 360 like both cats and dogs. How many students like neither cats nor dogs? So we can kind of think about this using a Venn diagram. Oops, that's not what I meant to do. Just want to drag it over here. Okay. So let's say in this Venn diagram, our left one is going to represent cats, or cat likers, and then dog likers. My dog is right here, by the way, so if you hear anything walking around my iPad, that is my mom's dog. And let's say that inside of this whole thing, we just have everyone who took the survey. So there's 1,000 total in this bubble, and inside of the cat bubble there are 530 total. Inside of the dog bubble there are 740. And we also know that in the middle, people that like both cats and dogs, that number is going to be 360. So if we want to know how many students like neither cats nor dogs, we're basically interested in how many students are outside of these two bubbles, but inside of the survey bubble. So if we knew that there were, if we knew how many people were exclusively in this bubble and exclusively in this bubble, then we would just add that to this, and then we would get how many people are in the two bubbles combined, and then take that away from 1,000. So that's what we're going to do. So we know that 360 are in this little intersection here, and 530 lie in this total bubble. So I can just do 530 minus 360 to get how many students are in this little moon area, right? People that like cats but don't like dogs. And this is equal to 170. So let's maybe put that in black. Same thing for dogs. There are 740 students who like dogs, and 360 of them like cats. So there are 380 of them that don't like cats. This is how many people like dogs. This is how many people like cats and dogs. This is how many people just like dogs. Okay, now let's add these numbers up. So 170 plus 380 plus 360. What does this equal? 7 plus 8 is 15. 15 plus 6 is 21. 3, 6, 9. So this is equal to 910. So within this giant pair of bubbles combined, there are 910 students. And notice that we could not just add 530 to 740, because then we would be double counting everything in the middle here. So there are 910 inside of those two bubbles, and so there are 1,000 minus that, which is equal to 90 students outside of the bubble. So put 90 right there. So 90 students don't like cats or dogs. Let's do another survey. This one will be a little bit more involved. So let's say that there are 700 students that are polled. 320 of them like rock music, 310 like rap, 410 like pop. There's also some information about people that like two types of music. So 160 like both rap and rock, 200 like both rock and pop, and 180 like both rap and pop. Also, 120 students like all three. I would like to know how many students like exactly two types of music. And then as a follow-up, how many people like none of these three. So again, we're going to do the Venn diagram approach. So let's, yeah, okay, I'll do this here. Duplicate, duplicate, duplicate. And maybe I can move this up a little bit. Okay, I think that'll do just fine. All right, so then let's label these. This will be rock, this will be rap, and this will be pop down here. Okay, so there are going to be 320 total in the rock bubble. There are going to be 310 total in the rap bubble, and then 410 in the pop bubble. There are 120 students that like all three, so that's going to be the very middle there. 160 total are going to like both rap and rock. So rap and rock, that's going to be this intersection right here. So this intersection is going to be 160. And 120 of them also like pop, right? So if 120 of them also like pop and I need 160 total in that intersection, then there's going to be 40 left over. So let's put 40 for that intersection right there. Let's do a similar thing for rock and pop. Rock and pop would be this intersection, and that intersection there should be a total of 200. And so if we're splitting 200 into 120 and something else, that something else should be 80. So there are going to be 80 students that like both rock and pop, but not rap. And then what about people that like rap and pop, but not rock? That would be this little bubble here. So rap and pop, there's 180 of them, and 120 of them go here. So we'll put 60 over here so that makes 180. 60 there. Okay. So how many students like exactly two types of music? We're now ready to answer this. These people like exactly two. These people like exactly two. These people like exactly two. These people like three. These people like one, one, one. So we'll just do the circled ones. So we'll do 40 plus 60 plus 80, which is equal to 180 students like exactly two. Two types of music. And how many like none? All right, well, this might be a little bit trickier. I think that we need to get a little bit more information. So we'll do a similar strategy to what we did before, where we'll have like an overall bubble of everyone that was polled, and then we'll just subtract everyone that's inside of here. So we need to know how many people are in rock, but not in the rest of that part of bubble. And then similar thing for people that only like rap, and then people that only like pop. And then we'll just add all of the numbers together and subtract that from 700. Okay. So 320 total, and then we just need to take away these. So what's 320 minus all of that? So 320 minus 40 plus 80 plus 120. That's 320 minus, that's 240, I believe. Yeah, because this makes 120. 120 times 2 is 240. So this should be 80. So there are going to be 80 students out here. I'm just going to go ahead and let's just like highlight that, I guess. Okay, what about for rap? So we'll do 310 minus these three numbers. So 40, 60, and 120. That would be 310 minus 220, which equals 90. So we'll have 90 here. And then for the last bubble, we'll do 410, it's this, minus these three numbers, 80, 120, and 60. That's 410 minus 260, which is equal to 150. So we'll have 150 down here. And now we just have to add all of the numbers that are highlighted together and subtract it from the total number of students surveyed, which is 700. Okay, let's add all those up. So 80, 40, 90, 120, 80, 60, 150. Okay, these two make 200. 40 and 90 and 80. 40 plus 90 is 130, plus another 80 is 210. This is also 210. So adding all of that up gives us 620. Okay, so there's 620 students in the bubble, and then 700 minus 620 students outside of those three bubbles combined. That gives us 80. So 80 students, like none. All right. So what we've been using sort of implicitly so far is something called sets. And sets are just groups or collections of objects or things or whatever. And the things inside the sets, we call them elements or members of the set. So in the previous example, we had the set of students who like rock music. We had the set of students that like rap music. We had the set of students that like pop music. And then we were looking at sort of like intersections and unions of those sets and so on. I'll define those things a little bit more later on when we start using them more. But yeah, so we can write sets in different ways. So we can describe them verbally, like I could describe like, the set of all the four seasons. How we often write sets, if we're not just like describing it in words, we would use these curly brackets. So not specifically not parentheses, not square brackets. We specifically are using the curly braces to denote sets. And then we just put whatever elements or members that we want in our set. So here we just have like the four seasons. The order doesn't matter with these at all. So if I just wanted to write these in whatever order that I wanted, summer, winter, fall, spring, or summer, winter, spring, fall, or fall, spring, summer, winter, order does not matter. Those sets would all be considered the same because they have the same things in them. The order is not particularly important. All that we care about is whether or not something is in the set. One basic thing that we care about with sets is how many elements that we have in the set. We call this the cardinality of the set. And for the previous set of like the four seasons that we had, we would say that the cardinality is 4. The notation that we use to describe that we would just put our set over here, and then we would say n parentheses of that set equals whatever the cardinality is. So n stands for number, so like the number of things in the set A is equal to 4. That's how I sort of like read this in my head. Other books will use like different notation for the cardinality. This is going to be the one that we'll stick with just because n of set, number of things in set, just kind of makes enough sense for us. So, all right, so let's say that R is a set of UConn students who like rock music, and P is the set of UConn students who like pop music. Okay. How do we describe the set of students who like both rock and pop? So we've already kind of seen like you could do like a Venn diagram thing. If we have like the rock students over here and the pop students over here, then in the middle, like the overlap would be the students who like both rock and pop, right? We describe this like in words as like the intersection. So like the two sets are intersecting. So we would say the intersection of R and P is R, and then we'll write it like this, P. So I'll literally read this as R intersect P. So like this symbol right here, it's just the intersection symbol. So I just literally read it as R intersect P. We can also describe sets of students who like rock or pop. So here we had R intersect P. What we'll do here is R union P. And careful with like how you write this. This is not like the letter U. Put it in red because it's just specifically not. That's how I write my U's. This union symbol is different from how you write like the letter U. It's literally just like the upside down of this thing right here. So don't. This is kind of like a pet peeve of people that do a lot of set theory. Don't write your union symbols like the letter U, even though like it is, kind of meant to look like the letter U. I don't know. It's not that important. Anyway, visually, what's going on here with the union? Let's go back to blue. This is when we just take all of the things that are in this set, or in this set, and then just combine them. So everyone that likes rock or pop, just somewhere inside of this bubble or these two bubbles combined, this would be the union. So this right here is our union P. And then if I wanted to describe our intersect P, that would be the things that are inside of both of them. Okay, so let's say that we knew how many students like rock music, we knew how many students like pop music. So let's say that we knew that the number of students in the set of students who like rock music is 500. In other words, there's 500 students that like rock, and then there's 600 students that like pop. The number of students in the pop set is 600. What can we say about the number of students that like rock and pop, and the number of students that like rock or pop? So this is the number of students in R intersect P and R union P. So this is R and pop, rock and pop. This is rock or pop. So just visually again, R, P, 500 here, we have 600 here. Depending on how much overlap there is, we can say certain things. So at minimum, if I were to combine these two things, it could be the case that everybody that likes rock also likes pop. So it could be like one of these situations, something like that. So everyone that likes rock also likes pop. And then there's just like another 100 students out there that only like pop, but not rock at all, right? So that's possible. So we can say that as far as the union is concerned, it has to be at least like at least 500, because there's at least 600. Because there's 600 people that like pop, and maybe all of them also like rock. So at minimum, there's going to be 600. And at maximum, it could be that there's no overlap between the two sets. So it could be like one of these situations where they're just totally distinct, and then there would be 1,100 students total, right? Moreover, we could say, like, let's say that like we knew how many students were in the middle here. Let's say that we knew that there were like 100 right there. Let's just pretend we knew that this was 100. we could actually just figure out exactly what this is. Because this would just be, well, you could just take, you could do it similar to how we did it before, or you could think of it like this. Just take 500 plus 600, and if you do this, let's see, so you do 500 here, and then 600 here, and then you notice that we're double counting everything in the middle. So let's just take that away. So to compensate for double counting. So we do 500 plus 600, and now we've double counted the middle 100. And so we would be left with 1,000 total. And so this is called the inclusion-exclusion principle. It states that for all sets A and B, the number of students in A union B is equal to the number of students in A plus the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. So this is like number of students that are in both sets, number of students in A plus number of students in B minus that intersection. And so like the idea is exactly the same. You have A, you have B, and then A intersect B in the middle here. You just take all the elements in A, add it to all the elements in B, and now you've double counted everything in the middle, so you just subtract it once to compensate for double counting. So revisiting that survey from the beginning, we had 1,000 students surveyed, 740 like dogs, 530 like cats, 360 like cats and dogs. So we could say that the number of students who like dogs, so D is going to be the set of students that like dogs, is equal to 740. Number of students that like cats, number of students in the cat set, that would be 530. And then number of students that like both, so this would be students in D intersect C, this is equal to 360. Now we don't have to do anything with like Venn diagrams at all. Like we could just say that the number of students in D union C, the number of students that like cats or dogs, is equal to 740 plus 530 minus that intersection, 360. And what's this equal to? This is 1270. 1270 minus 360 is 910. And so there are 1,000 total. 910 of them like cats or dogs. So if I want number of students that like neither, then I would just do 1,000 minus 910 to give us our final answer of 90. I'll let you try the following one. We're just applying inclusion and exclusion. So we've kind of gotten rid of some context here, and we're just saying like the number of things in one set is 15, number of things in another set is 12, and we know that the number of things that are in the union of those two sets is equal to 23. Find the number of things that are in the intersection. I'll give you a couple seconds to pause and then try this problem, and then come back when you are ready. Okay, so here I'm just rewriting the inclusion-exclusion principle. And now I have 3 bits of information. I just want to throw those bits of information into here and then solve for the last bit of information. So the union contains 23 elements. A has 15, B has 12 elements, and we don't know how many are in the intersection. So we have 23 is equal to 15 plus 12 equals 27 minus n of A intersect B. And then solving for that, what do I have to subtract from 27 to give me 23? I have to subtract 4. So n of A intersect B is equal to 4. There are 4 things in n intersect in A intersect B. Okay. Inclusion exclusion works just the same using percentages as well. Looks slightly different. So just a little bit of notation. P of A is just going to represent the percentage that A makes up of the total population. And using this, we get the percent inclusion exclusion principle, which states that for all finite sets A and B, P of A union B is equal to P of A plus P of B minus P of A intersect B. So these are all, instead of saying the number of things in A union B, it's like the percentage of what A makes up of the total population plus the percentage that B makes up of the total population minus the percentage of what's in A and B, etc. By the way, I forgot to mention this earlier. What is a finite set? Finite set is just something that only has, like, it doesn't have infinitely many things in there. Obviously, like, these statements would not really make as much sense. If you had an infinite number of things in one set, then, you know, if you're doing, like, the original one with, like, and stuff like that. Even percentages, like, doesn't really make as much sense if you just have an infinite number of things in a set. So it just makes sense to not look at infinite things. So let's see an example of the percentage inclusion exclusion, and then that'll wrap us up for this video. So a survey of students found that 60.2% of students like dogs, 52% like cats, and 10.8% like neither cats nor dogs. How many students like both cats and dogs? So if you're feeling confident, I would recommend, again, pausing the video, trying the problem, and then unpausing, see if you get the same thing. If not, I'm just going to kind of go ahead and do it. All right, so the percentage of people that like dogs is 60.2%. Percentage that like cats is 52. Percentage that like neither cats nor dogs is 10.8. So we don't really have notation for neither cats nor dogs here. So I can't really say something necessarily. So let's maybe come back to this a little bit. Or let's just think about how do we apply this information that 10.8% neither like cats nor dogs. Well, if that's how many students like neither cats nor dogs, then like what's left over of that out of like the total 100%, that would just be counting like the percentage of students that like at least one of like cats or dogs. And so that would be C union D. So students that like cats or dogs, that percentage would be just take 100% of the population and take away the 10.8% of students that don't like either of them. And then you'll be left with students that like cats or dogs. Okay, this is equal to, well, 100 minus 10 is 90. Take away another 0.8, you're at 89.2%. Okay, so the percentage of students that like cats or dogs is this. We can also use inclusion exclusion to say that percentage of cats union dogs is equal to percentage that like dogs plus percentage that like cats minus the percentage that like dogs and cats. And this is what we're looking for, so this is good. So this we now know is equal to 89.2. This we know is equal to 60.2. And percentage that like cats is 52. So now we just kind of solve for this. 60.2 plus 52 is 112.2. Now we just solve for this. We'll add this to the left-hand side. We'll add it to both sides. And then I'll subtract 89.2 on both sides. So on the left, I'll have P of D intersect C. And on the right, I'll just have 112.2 minus 89.2. What is that equal to? That is equal to 23%. Okay, so this would be our final answer. 23% of students like both cats and dogs.